Look at this coordinate grid as we apply a standard matrix transformation. As the space stretches and skews, you can see what happens to almost every vector. They get knocked off their original trajectories, their lengths change, and their directions rotate completely. But watch closely as the space moves. A few specific vectors stay locked on their original paths. The transformation flows right past them. They might stretch or shrink, but they refuse to rotate. These unmoving pathways are called eigenvectors, and the exact amount they stretch along that path is called the eigenvalue. Take a simple scaling matrix. A vector pointing straight along the x-axis gets multiplied by 2, extending its length without tilting. A vector on the y-axis scales by 3, also keeping its direction perfectly straight. These lines are not random. They represent the natural axes of the transformation itself, revealing the exact framework the matrix was built around. We can capture this geometric reality with a single equation, A times V equals lambda times V. Applying the entire complex matrix transformation to our vector gives the exact same result as simply multiplying that vector by a single number, lambda. To find these hidden vectors, we move everything to one side, setting the equation to 0. Here we hit a mathematical wall. You cannot subtract a plain number, lambda, directly from a matrix, A. To fix this, we multiply lambda by the identity matrix, I. This translates the scalar into a matrix format, allowing us to factor out the vector, V. For this new equation to equal 0, without the vector itself being 0, the combined matrix term must squash the entire coordinate plane into a lower dimension. A matrix only collapses space when its determinant is 0. By calculating the determinant of A minus lambda I, we arrive at the characteristic equation. This formula identifies the exact values where the matrix behaves as simple scaling. Let's run a specific matrix, 3, 1 over 0, 2. Plugging this into our characteristic equation and solving the resulting algebra leaves us with two clear numerical values, lambda equals 3 and lambda equals 2. When we plug lambda equals 3 back into our equation, the y-coordinate zeroes out. This draws a perfectly horizontal vector on our grid. Apply the same logic for lambda equals 2. The algebra resolves to x equals negative y. This maps out a second vector, shooting diagonally across the space. We now have both vectors sitting side by side on the same coordinate plane. One stretches by a factor of 3, the other by a factor of 2. Completing this algebra proves that the chaotic movement of any matrix can be entirely mapped by finding these calculable foundational pathways. Watch what happens to this transformation grid when we shift our perspective to align perfectly with the eigenvectors. The dense, complicated matrix immediately simplifies into a clean diagonal matrix, leaving only the eigenvalues behind. This process is called diagonalization. By working strictly along these natural axes, complex matrix transformations turn into basic multiplication. Computations that would normally require massive effort are eliminated. This principle scales to enormous datasets. Google's PageRank algorithm models billions of interacting web pages as a single, sprawling matrix. Because the matrix models how traffic flows between sites, the primary eigenvector points. That stable point identifies the most authoritative destination in the network. Engineers apply the same logic to physical structures. When calculating the stability of a suspension bridge, they find the eigenvalues of its stiffness matrix to determine the specific frequencies where the structure will critically vibrate. Finding these values allows us to identify the underlying structure in complex systems, whether we are ensuring a bridge stays stable or ranking the entire internet.